Good afternoon, everyone. My name is Graham McAllister. I'm a senior principal engineer at AWS. I guess we're called technologists now, which I still like engineer better than technologist, but I guess I'm just old-fashioned that way. Not going to really be talking about AWS today. We're going to be just talking about standard Postgres. This is a talk about sort of practical memory tuning, so it's not going to go ridiculously deep, but it's more of trying to give you an idea of how Postgres uses memory and how to think about memory if you're using Postgres to kind of get the most effectiveness out of running Postgres. So, I always start with try to be like, why do you care about memory tuning on Postgres, right? Well, to just show you, I ran this benchmark, and it's just a read-only benchmark. It's fairly simple, point selects. And the green is sort of a normally tuned Postgres system, right? That's running well within its memory. And the red line is a system that's got less than optimal tuning. And what you see is we have an 11x reduction in throughput based on the system not behaving correctly, right? So that's kind of bad. Part of the reasons, like the first little bump there, is because the buffers that you want to read are not in memory, so you're going to disk for them. Over here, you're actually swapping, so you're thrashing the box back and forth, and you're actually getting down to almost 0 TPS, right? So this is quite bad, but it's actually not the worst case scenario. The worst case scenario is the killer, is the, out-of-memory killer on an OS, in this case Linux, right? So that's the thing you really want to stay away from, because then you really will be at 0 if that kicks in. So we'll get into a little more about that, but this is why you should care. So what is the out-of-memory killer? So in Linux, which is predominantly where most Postgres runs, the out-of-memory killer is the OS's way to make sure that it doesn't basically lock up, and it'll kill off things that use too much memory. So if we have these Postgres processes, and if the size of them sort of represent how much memory they're using, how many people, if we're running out of memory, which one do we think we're going to kill here? Probably 4, right? That would seem like the obvious choice, right? No, it actually would be 3. And the reason it's 3 is because the badness score is a combination of how big your memory is and how recent your usage is. So if somebody expanded, if 4 was large for a long period of time and then 3 came along and asked for memory, then 3 is going to get killed. So that's, it's basically, you're not going to understand. Like when something gets killed, you're going to be like, oh, something randomly, like it almost looks random. It's not, but it looks random, right? That 3 gets killed. The problem with 3 getting killed is if 3 is in a critical section at that point, not only does 3 get killed, but you have to restart your whole Postgres environment, right? So this is something you really want to avoid if possible. So I tell people, how do you stay away from the memory killer? Well, one of the ways is to use swap. And this is sort of controversial. Not everybody agrees with using swap, but I think using swap in a minimal fashion is actually really useful. So normally if we have a request and there's free RAM, we just solve it, right? But if we ask for more RAM once we're full, that's where the killer would kick in, so we don't want that to happen, right? So instead what we're going to do is we're going to set up swap, and then to try to fill those 4 chunks of 4K, we're going to swap those out, make room, and we're going to be able to fulfill our request, right? Now this is obviously going to be slower because that has to happen. Swapping out to even, to storage is going to be slower, but your database didn't crash, right? So this works okay. And that's what you're calling swap out, right? But at some point, if those blocks in green that are now in the swap need to be used, you're going to have to swap those back in, right? If this is happening too frequently, you have what's called thrashing, right? And this is why you don't want a tremendous amount of swap. Like even with a 64 gig box, you probably only want a couple gig of swap, because if you have 64 gig of swap and you've swapped out your entire memory, the chance that you need a lot of that memory back in is going to be high, and you're just going to be in this thrashing thing. So a little bit of swap's okay, and that's how we run most of our systems. So let's look at an overview of how Postgres uses memory. So here I'm just showing the overall memory for the box. The pink isn't the operating system. It needs some space for the kernel and other things. And then one of the big users of memory sort of on Postgres is the shared buffers, and this is the caching of your data blocks. And on something like RDS and a bunch of other databases, typically we set this to like 25%. Then there's the Postgres processes, every one you spin up. It's going to take some RAM. And then there's the elephant in the room. Not that elephant, but the page cache. And the page cache is the thing that really distinguishes Postgres from other databases in that it uses a secondary caching mechanism. And this is both good and bad, and we'll get into that. On other databases, like if you come from SQL Server or Oracle, Or what we do in Aurora ourselves is that there's no secondary cache, and you just have a larger buffer, shared buffers, right? And this is typically around 75%. And we'll get into sort of the pros and cons of that, but that's just to contrast, this is the difference between Postgres and other databases. So the page cache is interesting, right? Because if you ask for a read, what's going to happen is you're going to look in shared buffers, and if it's not there, it's going to look in the file system page cache, and if it's there, it just returns to the shared buffers, and then it gets read as normal. If it's missing, then it has to go to storage, into the file system cache, and into shared buffers. So you'll notice that there's probably some duplication already, right, happening here. Also, when we do archiving of wall, or writing wall, or archiving of wall, that all goes through the file system cache. So what your file system cache actually looks like in the end is a whole mix of a bunch of different use cases, right? So you've got some shared buffers, like some blocks that are being cached there, some random files, miscellaneous things. The interesting thing is, when there's pressure, like if some of the miscellaneous, someone does some big VI of a 2 gig file on the box, that's going to need file system cache. What that's going to do is possibly push out a whole bunch of your shared buffers, right? This is going to change the behavior of how your database is running. So this is sort of one of the challenges with page cache is that you got to be careful about using other things on the box because you'll actually destabilize your database. So the whole thing about caching is we want to make sure that we've got the important stuff in memory. And to do that, we kind of have to understand for our database what the working set size is. And this is the stuff that we really want to have cached that we're going to hit often, right? So if I have this table, it's a whole bunch of orders, right? And it's 800 gig. You might think the working set size is 800 gig, but in fact, it's not typically because really we're only looking at the orders for the last year, maybe year and a half. So it's probably more like in the 80 to 100 gig range, right? So your working set isn't necessarily the size of your tables, right? But you really have to kind of understand your application because if you have a different table that's like inventory by, airport, it's going to have heat in each one of those and cold items in there as well. So this one might be, let's say, 200 to 400 gig as opposed to 80, right, for the same size database. So you kind of have to look at your system, right? The other thing to think about when you're thinking about working set size is sort of randomness. So if we take a table here that has an index and a heap, and we start doing accesses, and if they're random, we're going to touch a bunch of different pages in the index, and then we're going to get a heap page. Then we're going to touch another set of index blocks. You notice that root node in the index is getting warmer, right? But all the other ones are still pretty cool, right? And so if we continue to do this, we'll see that we need a lot of pages to be cached, but they're not getting hit very often except for that root one, right? So this can be very expensive if you've got a lot of randomness. It means your working set size is probably going to be larger. On the other hand, if you have right-leaning data, like let's say it's organized by a date, right, where you're inserting the current date, well, then what happens is you're just going to be working on that right side of the tree, right? So the number of blocks that you need to keep cached are much smaller, right? So this is one of those things to also understand is like how you're using the data. So let's dive in a little bit more into shared buffers. So this is sort of the typical configuration, right? You have shared buffers. It's 25%. You have the file system cache, which is probably 50%. The shared buffers are going to be very warm because that's the first place we look. And then part of the file system cache is going to be quite hot. And then some of it will be a little cool. And then there's just storage, which of course is cold because it's not a cache. So why don't we make shared buffers smaller or larger, right? Like what's the effect of like choosing a size? So again, a simple sysbench read-only point select. And this entire database fits in RAM through all this testing. But what we're going to do is we're going to experiment whether it fits in shared buffers or the file system cache, right? So when we start off on the left, and the pink line is TPS, so we'd like that to be high, right? And the green line is the amount of table data that's in cache, and the blue is the amount of index in cache. So we start off where we have 25% of the host memory in shared buffers with 80 tables. And so at this point, my working set size fits inside of that 25%, right? So it's all in shared buffers. We get a really good number, almost like 850,000 TPS here, and everything's in cache. So now, if I make that working set larger by, basically increasing that table by a little more than 50%, Now it doesn't all fit in shared buffers, just a little bit, right? And what we see is that the index is still all in memory, right? The blue line is still at the top. But the green line is dropping. We don't have enough memory to cache everything in the shared buffers. Remember, it's still in the file system cache. We just have to do an extra hop to get it. We can already see that we're decreasing the amount of throughput we're getting, right, in the pink line. And this continues. So we double again the working set size. So now even less data fits in shared buffers. Now, we still have a low index, but like for the table data, we're only about 30% of it fits in shared buffers. So we're doing a lot more accesses to the file system cache. We've dropped again, right? This kind of continues. As we increase the working set size, now we are pushing indexes out, right? These are the things that are hit even more frequently than the heap. So we have another drop in performance. Keep going further and further, right? And we get all the way out to here where very little of the data fits in shared buffers anymore because we've reduced shared buffers down to 1% of the size. So we've made it tiny, right? So almost nothing fits. So again, everything's still cached in the file system cache, but we're at 60% of the performance. So that means going to the file system cache frequently has quite an overhead, right? But, you know, as we can see on the left-hand side, it's not too bad if we do that somewhat, but if we're doing that for almost every time we need to get a block, that gets very expensive, right? So this is why you don't want tiny shared buffers. And to kind of show you this, how many people are familiar with the PG buffer cache extension? A few, yeah. So this is a really useful tool just to look at what's in cache. It is a bit expensive to run, like from a system utilization perspective, so I wouldn't run it all the time, but it is useful for doing these kind of diagnostics. So the usage count from 5 to 1, with 5 being the most hot in this case. What we see is when we're at 25% of host memory and everything fits, the index is like very hotly cached, right? Like we have a lot of 5s, which means the top layers of that index are very well cached, down to probably some of the leaf nodes that are less so. And on the table, we see the opposite, where the heap is more randomly hit, so therefore it's going to be more sort of spread out and more down at the 0 and 1 touch count, right? If we look at that 1% of host memory, we see that almost nothing is in cache, right? And even the stuff that's in cache hasn't been touched very many times, so it's going to be ejected very quickly, right? So we're spending a lot of time putting things in and out of shared buffers. So why not just have a big shared buffers then, right? That seems like the obvious solution to this problem. Well, the challenge with Postgres is that, again, if your Postgres process dies, your shared memory goes away as well, right? So at that point, this is what you're left with when you're restarting if you have a small file system cache, right? You don't have very much data cached on the system, which means when you start your shared buffers up, it's going to be cold and it's going to take a long time to warm up because it's mostly going to have to come from storage, right? So to solve this, like in Aurora, we made larger shared buffers, but we also made a survivable shared buffers. But that's something that I assume the community will do when it starts doing direct I/O and asynchronous I/O. So it's something that's going to change. But for now, setting shared buffers small is kind of reasonable. But the reasonable value is you want it to be large enough to contain most of the heat of your system. It doesn't have to be too large. It just can't be too small. So yeah, it takes a while to warm up. So hugepages is something that most people were pretty aware of if they ran Oracle or other databases as a way to get better performance for your database. But I like to cover it still because now that people are using containers and other forms of systems, they don't always set up hugepages because they're running sort of smaller systems. But it is really important to understand why hugepages is critical. So I have the shared buffers on the right, and we have the Postgres processes on the left. For them to map into the shared buffers, they actually have to have a page table entry. So when this Postgres process wants to access that 4K block, you get a little entry in the page table, right? That's the map. Now it gets one of those for every block it reads, right? So every time it accesses one, it's got to have a page table entry. If another process still wants to talk to that block or look at that block, it also gets a page table entry, right? So these are each for 4K if you don't run hugepages. If you run hugepages, now you're talking about one page table entry to point at 2 meg, right? So the critical thing here is if you're running with a lot of processes and a shared buffer where you access a lot of it, because it's not just that you have a large shared buffer, it's that the shared buffer is accessed by a lot of those processes, then you'll actually end up using a lot of RAM, and there's a lot of overhead of just going through that page table. So to demonstrate this, again, sysbench read only, higher better. The green line is with hugepages, and the pink line is with hugepages off. So what we see is that essentially for this number of clients with a 160 gig working set, you don't see much difference. You see a little bit of ramp up because there's a little bit of overhead on the smaller blocks for the page table, but you wouldn't probably care too much, right? But I ran the same benchmark, but now I've basically increased the number of clients from 250 to 500 here. And we see a dramatic performance difference, right? And this is because we're now using more RAM on the system, and we can't keep all the blocks in cache. And if I push it to 1,000 clients, what we see is that now I'm getting into that scenario that I talked about at the beginning, where we're actually swapping because we've pushed out so much RAM. To illustrate this, this is the cost of not using hugepages as a percentage of your RAM. So on the vertical axis, I have the page table size, so that's the yellow, or sort of tannish color. The bright yellow is the percent of host memory. And what we see is that, you know, you're using, even at 250 clients with this size of a shared buffers, you're using like 30 gig of RAM. But at the top end, you're now using 40% of your RAM for the page table entries when your shared buffers are only 25% of your box, right? So this just shows you that, like, there's, for small instances that are like a gig or two, huge pages is probably not a big deal. But as you get larger, just make sure that, like, you're on a system. You know, if it's a managed system, they're probably using hugepages. But if you're doing it yourself, make sure that you're paying attention to this, because at some point there's a tipping point where, hey, some new client comes in and adds another 500 connections to your database, and now your page table just doubled on your system and you've ran out of RAM, right? So let's talk about the other cluster-wide memory parameters. A whole bunch of these are actually new in 17. Up till now, Postgres actually hasn't had a lot of cluster-wide memory ones outside of shared buffers. I'm not going to go into too much detail, but these are actually really cool because a lot of these were fixed size allocations before, and we had a lot of customers who would have trouble with multi-exact, where they'd overrun and get a lot of performance issues. Now you can actually set these. The defaults aren't super large, so they're probably not a concern on most boxes. But just be careful about, again, this is new with 17, so if you go set these each to a gig or 2 gig, that's going to add up on your system, right? I'm not saying you should set them that large, but, my only thing about the max prepared transactions is, just don't use it, if you can, because prepared transactions are generally evil for databases, So the next one is that we're going to look at is per session operations. So for regular tables, our cache is shared buffers. That's the thing in front of the file system cache, right? And that's a global, as we said, so that's one allocation. But if you're creating temp tables in Postgres, then you don't use shared buffers, you use temp buffers, because temp table is local to your session, right? And so you need to have temp buffers. But the thing to note about this picture is, guess what? Temp buffers are still backed by the file system cache, right? So you typically don't need to make this very large, because if you spill, you're still just spilling to the file system cache, and it's going to be deleted right away, so it's not usually a big deal. So I tell people, you can test this, but for a lot of use cases, the defaults are fine for temp buffers. One of the funny ones that doesn't look sort of like it's a session level variable is logical decoding work mem. And so this is used when you want to stream stuff off, let's say to your data warehouse. For every logical decoding slot that you have, you're going to have a logical decoding work mem area that you're going to be using, right? So you get one of those. So when I say it's per session, it's like per session that you have pulling data from your database. So if you have 2 logical decoding slots, you have double the thing, right? And remember that logical decoding slots are per database. So if you've got 10 databases, you might not think, but then you have 2 people pulling from each database. Now you got 20 of these. So if you set this quite large, you could be using a lot of RAM. And it's the kind of thing, again, where it won't use the whole amount unless it needs it. But if someone puts a large transaction in, like a 1 gig transaction, that's going to show up on each one of those slots, right? So you might be running normally, someone commits a very large transaction that then has to spill, and boom, you're out of memory on your box, right? So this is another area to be very careful with. And the next one I think is like one of the most interesting ones that took me a while to understand when I came to Postgres is that there's per session and operation memory allocators. So here I'm showing workmem. So this is used for sorting, typically, hash joins, a bunch of other use cases. So to demonstrate this, and hopefully that's large enough for you guys to read, I set my workmem to 1 gig, and then I did this query that you can see up there, and it's just a generate series that forces a sort, right? I just, instead of building a whole thing. And what we see when we get the explain plan is that I spilled to disk almost 3.8 gig to do this sort, right? Because that's how big my system is. And it took about 9 seconds to run this. So you can see that generate series is exactly almost 3.8 gig, right? So that's why I needed that RAM. So this obviously couldn't sort in memory. And to sort of illustrate as we walk through this, I'm showing the amount of time the memory was used for and how big it was, right? So for this query, it's 9 seconds using about a gig for most of it, right? So let's go increase that workmem to 4 gig, right? Because we know if we go to 4 gig, this should sort in a single pass, which it does. Yay. And it's much quicker, right? Now it's down to 3 seconds. So this is an interesting trade-off when you think about it, right? Like we've used a lot more RAM, but for less time. So it's probably okay, right? It's probably worthwhile in some cases. Now to make this more challenging, still the workmem set to 4 gig, right? But now my query has gotten more complex. I now have 2 3.8 gig sorts, right? And then I order those together. And so what we see here is I used 4 gig there. I also used 4 gig here, right? So every operation in Postgres can use up to the workmem, right? So if you have 20 sorts in your query, you could use 80 gig of RAM, right? So, then there's a little extra memory for sorting this all together, right? So this took like 7.5 seconds. But yeah, see what it used? It went up to like 9 gig. Yes?
You said a threshold on the number of processes or something like that?
Nope. I mean, it's one process. That's the whole thing. It's just one process doing this. Like this isn't, this is
Not parallel. You don't have
not parallel. That's not parallel. That's just like per operation of like, so if you do 20 sorts, you got to be really careful, and you got to think of workmem as a per operation number, not as a, for a lot of databases, it's like that's how much you could use for that session for workmem, but that's not how Postgres works, right? So that seems a little scary, right? But I like making things even scarier. So we set our workmem to 4 gig, right? So it still have that 3.8. But then now we're going to join that with an 18.8 gig generated thing that we're sorting, right? So of course, the one sorts just fine in memory as we see, right? 4 gig. But this one goes to disk because of course 18 gig is bigger than 4, math. And then we have a final sort that's still not too big. So this takes 55 seconds to run. It sounds kind of bad, right? But it's even worse because look at how much memory we were using that 9 gig the entire time, right? So it's not just that, once you're holding that RAM, if you're doing other stuff with the query, you're holding that RAM until the query finishes. So this can be very expensive, right? So you can imagine someone thinking, oh, like, I'm going to have a quick query. It's going to come in for a second, pop back out, and now for a minute later, it's used a ton of RAM. And if another one of these comes in, boom, you're in trouble, right? So one of the nice things that Postgres added a while back was this thing called hash mem multiplier. So this is used when you do hash joins, because before, if you wanted your hash join to stay in memory, you had to increase your workmem. But if you're increasing your workmem on your session, then you have all the risks that we just talked about, right? So the nice thing is you can set that. The default is 2. So here I have my workmem set to 1 gig, and I'm basically doing a sort. And this works pretty well, but I do 8 passes, right? So that means it's not big enough to hold it in one pass. If I go to 2 gig and I change the multiplier back to 1, basically it's going to take exactly the same amount of time, right? Because all I've done is it's just multiplying those two things together, 1 by 2, 2 by 1, right? So no difference. But if we do set the multiplier to 8 and the workmem to 2, right, then it actually does it all in memory on a single pass, and it's a 75% reduction in memory. So this is a nice parameter, But do realize that it will increase the amount of RAM you're using for hash joins, but at least it doesn't risk you generally on your work mem. So those are ones that you just got to be careful about, like in the query when they run.
Same thing applicable for per session also. It's like or per sort order. Suppose if you have multiple hash join in the same query.
Yeah. You would get you will get multiple usages of memory. Yeah. So all those things that use work mem in any way stack up. Yeah.
Other than the paper and pencil, do you ever have a system where you can kind of spec out so you can see like what the potential damage is going to be?
No, I mean I think it's a thing we've been discussing as a community is about how to like sort of get constraint on this. There's a couple different ideas. I was talking to Thomas Monroe about this in Europe here a couple of weeks ago, about some system to sort of like not allow excessive allocation. It's still kind of coming, but I think you'll see in the next couple of versions there's definitely a push for this now. One of the nice things I think about having a whole bunch of the databases as service providers having committers and being more involved is that some of these issues that probably were happening but weren't as obvious to the development community are now being surfaced by, and so I think we're starting to work on these things. So hopefully over time this gets better. Yeah. 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 So, yeah. So I think you'll see Postgres moving towards sort of that model. I mean, it is kind of funny working in Postgres where it's a very good database, but there's some features that, just arrive in Postgres that I'm like, oh, wait, how long ago was that when I used that in Oracle? It was like 20 years ago. It's like, okay. But, it is, getting to be more enterprise use, so it's getting pushed. There's also per session items. So an example of one of those is prepared statements. So you can prepare a statement so it's faster to reuse. This is usually with a bind variable. So you're saying, hey, I've got this very specific one. It's just selecting from a table where ID equals $1, right? And when you do that, you basically allocate 4K for each of those prepared statements. So if you prepare like a slight variant of that statement 3 times, you're going to use 12K, right? This exists for the life of the session. So this is really important. There's a whole bunch of things that you will allocate in a session that won't go back to the system until that session goes away. So what I tell people is if you're using connection poolers, one of the good things with Postgres and really most databases is to make sure you're sort of trying to cycle through your connections on like an hourly or daily basis so that this memory usage doesn't just continue to bloat, right? Now, what was interesting, we had a customer who they were using our system and they were calling up and going, it just keeps crashing after like 5 minutes. We couldn't figure out what was going on. And what it was is that they had accidentally, on their prepared statements, they were preparing them with literals. So every execution was a new prepared statement. And so what you can see here is if you just run, I did 10 million prepared statements, and it only took like 5 minutes to put that in, and it used 90 gig of RAM on the session. And you think, oh well, no one's, that would just be a mistake. That's not going to happen to my system. But if you think about having 10,000 clients that have like 1,000 prepared statements each, they will also be using a large amount of RAM, right? So it is a thing just to be careful about where it adds up. Again, if you got 5 sessions, no worries, right? If you got 10,000, it's a different problem. Although if you have 10,000 sessions on Postgres, you probably have other issues. So, yes. I think so, yeah. Yes. So the other area is maintenance work memory. So this is like work mem, but for doing things like index builds, vacuuming, all kinds of stuff, right? So you set maintenance work mem to 1 gig, and you create an index, right? You can set it to 2 gig, you can create an index. Set it to 4 gig, create the index. What you'll notice is that what's interesting is, in this case, the index took basically the same amount of time. And the reason for that is we are spilling on this index build, but we're spilling to the file system cache. And so because of that, like as long as there's, it doesn't really make that much difference. Now, if you make that work mem the maintenance work mem too small, then you're spilling too many times, but like around a gig is probably fine for a lot of indexes. Like you don't typically get a lot more benefit. So again, this is if you're using a file system cache. The other big area where maintenance work mem comes in is vacuum. So just to run over this quickly, vacuum, when it's looking for dead tuples, it has to scan the heap, and there's now bits that help it do that, so it doesn't actually scan it, it just goes finds them. And it collects all those dead TIDs, right, which are basically, in this case, a block and an offset in the block, right? And that all has to fit within the maintenance work mem size, right? And if it doesn't, then you have a problem, because afterwards you're going to scan the indexes looking for those dead pointers and clean them up. So if you don't fit into the maintenance work mem, you have to do multiple passes on those indexes, which can be very expensive because many times the indexes get bloated. The more bloated they get, the longer vacuum takes, the longer it takes to scan them, and so you can get into kind of a really negative cycle. Now you'll notice I've got maintenance work mem up here for vacuum, but it's versions 12 through 16, because hopefully no one's running a version that's older than 12. You know, I'm hoping, because 11's now deprecated, right? So, I'm mentioning this because there's some changes in 17 that I'll talk about in a second. So we did an update, and I updated basically all the rows in this table. It's 500 million rows, right? So we got 500 million dead things that we got to go clean up. Got my maintenance work mem set to 200 meg. What we see is we have to do 15 passes on the index. So that's not good, right? But OK, fine. So again, the memory we needed, right, is 6 bytes per dead item. So it's 4 for the block, 2 for the offset. So 500 million times that is basically 2.8-ish gig, right? So hey, I'm a smart guy. I can just go change my maintenance work mem to 3 gig, right? This is going to solve it. I'm going to get a single pass on the index, right? Nope. 3 scans. So why is that? Well, as it turns out that Postgres up to version 16, or including 16, only could use 1 gig of RAM for this. So it didn't matter what you set it to above 1 gig, it only ever used 1 gig. So not great, right? No real option there. You just got to deal with it. So you really didn't want to have this many dead tuples in your table, right? But 17, and I say 17 plus because this will apply for everything after that. We set the maintenance work mem to 200 meg, and we start this vacuum, and it only takes 3 passes. Remember, it took 15 on the previous one. So what's changed? Well, with 17, they've changed how the memory is. So now it's 4 bytes per block, but it's a bitmap with an offset for the offset. So it doesn't use as many bytes, right? And in this case, I only needed between 400 and 600 meg for this vacuuming. So it was like a 5x reduction in the amount of memory required to do this, right? So that's really impressive. But let's kind of try a different update. So in this case, I'm doing an update where I'm setting, I don't know if you guys can see this, but I'm setting kind of a really weird thing where the CTID is equal to something. What I'm doing here is I'm updating every block, but only like some of the tuples in each block, because I want to make sure I touched every block. So you can do this with a query like that. So maintenance work mem 200. And you can see I've updated, what does it say, 58 million instead of 500 million. And the index scans, we got only 2, right? And this is because I only did 58 million, and I needed times 6, right? Now let's go to 17. So on 17, same thing, 200 meg, but we're back at 3. This is the same as what we had when we were doing 500 million rows, right? And that's because I'm still touching every block, right? So I don't have very many offsets, but I got all the blocks I still had to update, right? So let's look at this in a little more detail. So we have 2 workloads, A and B, right? Workload A updates rows all over the place, these 6 tuples. Workload B updates 1 block, right? In version 16, workload A requires 6 bytes times the 6 tuples. And in workload B, also 6 by 6, right? So 36 bytes. In workload A, version 17 needs 4 blocks times 4 bytes plus some space for the bitmap, right? But if you got workload B, now it only needs 1 times 4, right? Plus the offset. So it's going to be much cheaper. So where you're going to see the benefit for 17 is if you can keep where you modify the blocks down to a narrower range. Sorry. So maintenance work mem, 1 gig, 5 scans, right? This is 17. Excuse me. So we used between 4 and 5 gig. 17 plus, maintenance work mem set to 5 gig, 1 scan, right? So here we can see that the nice thing is we actually use all the memory you can set now. So you can vacuum much larger than you used to be able to do. The other thing with 17 is how it allocates memory. To show this, I vacuumed 50 tables in parallel with a 1 gig setting. But there's only 5 million rows, so we don't actually have a lot to vacuum. 16 used 11 gig to do this. See the sharp allocation, right? 17 only used 300 meg because it allocates now much smaller increments. So it's much more efficient. The other thing you have to think about when you're vacuuming, the parallel setting doesn't actually change the memory usage that much. Because it only affects the index scans. So it doesn't really change much. On the other hand, if you're doing auto vacuum, you do have to think about the number of workers you're running. Oops, sorry. Because if you have 30 workers and they can use 1 gig, you could use 30 gig up at once. And again, they won't use it if you don't need it. So if you don't have a lot to vacuum, you won't actually see that. But then if someone does a big backfill, you might see that. And so with that, this is where you want to stay away from. Hopefully I've shown you a few things that help you think about this to kind of keep from thrashing or getting killed or just running poorly. Thank you very much. Sorry about my voice.